Welcome everybody, it is Mrs. Fisher. Today we are going to be talking about parametric equations. This is something that you have never talked about before, kind of like polar equations. This is a way that we can actually graph using three different variables. This is actually pretty useful because if you think about our world, it is three-dimensional. So we're going to start off by writing down the definition of what a parametric is. So it is basically defining both x and y in terms of a third parameter which is basically a fancy way of saying variable. And that parameter is usually t for time. All right, so we'll go over some basic examples. Just to give you an idea of what we're talking about, I want you to think about what these equations would look like with respect to time. So the way that this works is we define both x and y in terms of a third variable, t. So instead of having one equation, you're going to be given two equations. So if I say x equals t and y equals t, and then tell you that time is infinite. Basically, I want time to be all numbers. I want to know what that would look like if we graphed it. So there's different ways you can do that. You can think about that in your head, or you could think about making a table if you wanted to. But your table now would have three columns. You could have a t, x, and a y. And you could think about different different values for time, and then think about what would happen when you substitute those values in for t, what you would get for x and for y. Okay, so if I substitute in -2, -1, 0, 1, and 2 for t in both of the given equations, what do you get for x? And then what do you get for y? Well, these are pretty basic equations, so you would just get -2, -1, 0, 1, and 2 for both x and for y. So then when I ask you, what would this look like if I were to graph it, I really want you to think about what would your normal graph look like. In normal graphs, we think about x and y as our normal rectangular coordinates. So what would that look like? It would look like the points -2, -2, -1, -1, 0, 0, 1, 1, and 2, 2. So if I actually plotted those points out, it would look like this lovely little line here. All right, and hopefully you guys are familiar with the fact that that is the equation y equals x. So what I gave you was parametric equations. So these are parametric equations. All right, and this is just your normal rectangular equation. All right, so another basic example would be giving you x equals 2t and y equals t, and then asking you to think about what that would look like. And again, this would be for infinite time. So again, you can kind of think about it in terms of what a table might look like, what it might look like if you were to graph it with respect to time. however you might choose to think about that. Some of you might just be able to think about it in your head. All right, but for x's, if we substitute in -2, we get -4. -1, we get -2. 0, you get 0. 1, you get 2. 2, you get 4. And then for the y's, we get -2, -1, 0, 1, and 2. So now what we're thinking about is what equation would create these x and y values. So if you think about plotting these points out, -4, -2, -2, -1, 0, 0, 2, 1, and 4, 2. So you should be able to see, oh, that's a line. Okay, and it's a line that has a slope of rise 1, run 2, and a y-intercept of 0. So this would be your rectangular equation. Okay, so again, I gave you parametric. So that's parametric. And this is rectangular. All right, now, hopefully you're saying, but there must be an easier way than plotting all these points. You're right. So there are easier ways. Okay, you can figure out what these would look like without having to do all the table work. So if I ask you to convert, or sometimes it's given to you by saying eliminate the parameter. Okay, basically what you would do, instead of, writing everything out, making a table and all that, I would just give you equations. So I'm giving you some more complicated looking equations here. Okay, and instead of making those tables, what we are going to do is basically put these two together by doing a substitution. So I'm going to pick one of these equations. I'm just going to pick this bottom one. I'm going to take that, get t by itself. So if I get t by itself, this is going to look like y plus 5 equals t. And then I'm going to take that y plus 5, substitute it into the top one. That gives us x equals 2. And instead of t, y plus 5, and then plus 4. And then if you simplify that, you get x equals 2y plus 10 plus 4. So x equals 2y plus 14. Now that is not what a normal equation of a line would look like, so we would prefer that you would go ahead and get y by itself here. So x minus 14 equals 2y. Divide by 2, we get 1/2 x minus 7 equals y. So that looks more like the equation of a line with y by itself. So you've eliminated the parameter in that you got rid of all the t's there. So you got rid of that third variable. Okay, so you don't have to make a table, you can just get rid of the equation there. Okay, so another thing you can do is look at more complicated equations. Now, more complicated equations, so I'm going to call this less basic. So of course, we always need to be a little bit more complicated, right? So we are going to find our own parametric equations in this example. So find x and y parametric equations that would produce a circle with a radius of 5. Okay, so the parametric equations we were looking at before all produced lines. They were all linear. So we need to figure out how we can take these parameters that we have and make them start curving. So this, hopefully you're trying to think about that on your own at home, but to get them to start curving, what we have to do is we have to throw in a trig function. Now this is going to tie into everything we've done this unit, which is why this is part of this unit. And we are going to call on the formulas that we've been using for vectors, for polar, and now for parametrics. So our x equation is going to be the same x equation that we've been using. X is going to equal r cosine, and instead of having theta, we're going to have our parameter t. So here the t isn't going to represent time per se, but it represents our parameter. So you can say t for theta if you feel comfortable with that. We are going to be dealing in radians, and radian, remember, doesn't really have a specific unit. It can represent any other thing besides degrees. So it can represent units of time. Y is going to be the same formula that we've been using, all units. It's going to be r sine, and then our parameter t. Okay, so hopefully that's going to be easy for you to remember. But when we throw in cosine and sine, it's going to start curving into a circle, just like our unit circle, just like going around with our vectors and with our polar, everything like that. So with this particular question, asking you to produce a circle with a radius of 5, 5 is your r value. So our radius of 5, that's going to be our r value right here. So the parametric equations are just going to be x equals 5 cosine, and then our parameter, and y equals 5 sine, and then our parameter. And so this particular circle is going to have a radius of 5, and I should have added on that it's also centered at 0, 0. If it's not centered at 0, 0, then we would have numbers added onto our equations here, added here at the end. We don't have anything added on the end, so it's centered at 0, 0. All right, our next example, we are going to adjust the equations to make an ellipse. Now, we haven't really talked about an ellipse yet in class, so some of you might be asking, what's an ellipse? So for those of you wondering, an ellipse is like this. So some might be saying, oh, you mean an oval? So the more mathematically correct term for that is an ellipse. So if you have an ellipse, it just means that it's not the same radius all the way around. So what do you think we would do to our equations from example 1 to make it not have the same radius all the way around? Now, they're not telling us specifically what to do, so if you wanted to make it be not a perfect circle, what you would do is you would just change one of the numbers in front. So change one number. That's what you do. So let's change our x value. It doesn't matter what you change it to. I'm going to change it to 8, let's say. So if we made x equal 8 cosine and y is still 5 sine, that would be an ellipse instead of being a perfect circle. Okay, so now what in the world are we actually doing, and what would this actually look like? And we can talk more about this in class, but I want you to see if you can check this out in your calculator. I want you to go in your calculator. I want you to go to the mode button. So go to mode. And in your calculator, under mode, you should see a section that gives you an option for function mode. And then there's a POL for polar. And then there's PAR for parametric. So I want you to select the PAR for parametric. I also, while you're in there, need you to select radian. You need to be in radian mode for this. Okay, so now when you go to hit y equals, you should notice that this looks pretty crazy. You're going to have an x sub t, a y sub t in your y equals button. You've never seen an x equals before when you hit the y equals button because it's a y equals button, but now you have an option for x equals. So now you can actually graph what we had in example 1 or example 2 if you just want to check those out. So if you want to type in 5 cosine t, when you hit your variable button that has the x on it, so type in an x, it now will show up as t in your calculator. And then you can do 5 sine t. All right, and then when you hit graph, you should see a nice little circle. If you want to check out the ellipse, pause the video to do all your graphing, but change the number in front to an 8, and you should be able to see an ellipse. If you want to make a more drastic ellipse, change it to like a 10 or a 12 or something like that. Okay, let's look at making a line segment. All right, you've never made a line segment before. So when I gave you the first examples, I was telling you that time is infinite. So if you are doing infinite amount of time, your parametric equations are going to make a whole line that go left and right forever and up and down forever. But with parametrics, we can actually tell the calculator to stop time, and we can graph just a little line segment in our calculator. So that's pretty cool. So I'm going to ask that we make a line segment. So make parametric equations. For the segment. That has endpoints. Five, 8, and -2, 7. Okay, so I want you to kind of think about this. 5, 8, and -2, 7. It doesn't really matter which one is your first endpoint, which one's your second endpoint. So I just want you to kind of sketch. Doing a bad sketch. -2.7 and 5.8. It's terrible. Let me try again. Down further. Okay, here's your segment. Now, in terms of time, we can connect the segment as fast or as slow as we want. We could have our calculator connect the segment like this slow, which I know you guys are enjoying how slow this is going because it's taking more time on the video. Or we could have it connected like this. Okay, it's all about how long does it take to get from point A to point B. We have control over how fast or how slow we want that to go. So we are going to choose our value for time. So choose the time value. Since you guys want the video to be shorter, I would think that we would want to choose time to be small. So I'm going to choose time to start at 0 and end at 1. All right, so this is how this is going to work to write our parametric equations. We are going to essentially have an equation for x that is going to look like mx plus b. It's going to look like a change in slope. Okay, so you are going to have a slope type equation that's going to look like change in x over change in time times time plus basically a point. It's your general setup for your x equation. Your y equation is similar. It's going to be a change in y over a change in time times your parameter t plus a point. And that point, I hesitate to call it like we always called this last number here the y-intercept. We called it the y-intercept because it was your starting point. So I'm going to call this the starting point. It's really your starting point for x and your starting point for y. So starting point x, starting point y. Okay? So this is what it's going to look like. Your x parameter, we want change in x over change in time. So look at your point A to B. How much does x change to get from A to B? So if we're at -2 and we're going to 5, what is your change in x? So from -2 to 5, your change in x is 7 units. We are choosing time to be 1 second because we want this done quick. So that's 1 second. So that's our change in x over change in time. So that's times t for our parameter, plus our starting point. So your starting point, you can either be at -2.7 to start with or 5.8. As I drew this, I started at point A and went to point B. So I started at -2.7. So my starting x was -2. So my x equation is x equals 7t plus, minus 2. So this is an equation that describes how my x is changing. The y, I'm going to do change in y. So to get from A to B, my y changes from 7 to 8. That's a change in 1 unit. in 1 second. And my starting y value was 7. So my final y equation is 1t plus 7. And I need to let the reader of my paper know that I've chosen time to be 1 second. So those 3 things that I boxed in is what I would need for my answer. So those are parametric equations for the segment that has those 2 given endpoints. So one equation describes what x is doing with respect to time, and the other equation's saying what y is doing with respect to time. Okay. All right, so I'm going to end with a Ferris wheel problem, everyone's favorite. So I want you to imagine that you're riding on a Ferris wheel. All right, so imagine we are on a Ferris wheel. And it has a radius of 35 feet. And the lowest point is 5 feet off the ground. All right, 1 clockwise rotation takes 12 seconds. All right, so what we are going to do is write parametric equations that represent our trip around the Ferris wheel. So we've got a lovely little circle for our Ferris wheel. Okay, here's the ground. This lowest point is 5 feet off the ground. Our radius is 25. Oops, sorry, that's 35. And 1 clockwise rotation takes 12 seconds. So we are going clockwise in 12 seconds. All right. So in this particular case, it might be helpful to think about your location with respect to time. If you don't want to think about your location with respect to time, you don't have to, I guess, but it might be helpful. We're not told, but let's assume that we're going to start here at the bottom. Okay, so at time equals 0, we need to figure out where we are. And then 3, 6, 9, and 12. Let's just break it up that way. So what is our x position and our y position at the different points in time? So at time equals 0, what's our x? So 0. And our y, that's at 5. At 3 seconds, 3 seconds is over here on the side. So our x position is at negative 35. And our y position is at 40. At 6 seconds, we're at the top of the circle. So our x position is 0. Our y position is 80. At 9, we are over here at the right, and so our x position is positive 35. Our y position is 40. Oh, that 80 is not right. That's 75. Sorry. And then at 12 seconds, we're back to the bottom. So we're at 0 and 5. All right. So to help you kind of figure out what your equations should be, it's really helpful if you plot what this would look like visually. Now, a lot of you were resistant to that when we were doing our sine and cosine waves before, but I would plot out what this looks like for x and what it looks like for y with respect to time. Okay, so if you think about what this looks like visually, at 0 seconds, 3 seconds, 6, 9, 12, and do the same thing for y. What does it look like? It's 0, 3, 6, 9, 12. Okay, so we have, for x, we have 0, 0. And then we have negative 35. And then back to 0. And then positive 35. Back to 0. And then think about what equation that would be. So hopefully when you look at that, you see, oh, that is a sine wave. It goes down to negative 35, up to positive 35. Your x-axis is actually time. So you should see that, oh, that equation would be x equals negative 35 sine t. Oh. And then for the y, I gotta go back and fix this because we have to do our period. 2 pi over b equals 12. And so we get 2 pi over 12 equals b, so we get pi over 6. So that's pi over 6 t. There. So our second one, let's see. If we graph that, for the y's, at 0, we are at 5. So we're off the ground at 5. And then we go to 40. Then up to 75. And then back to 40. And then back to 5. So we're going like this. So hopefully you look at that and you say, huh, that looks like a cosine wave. But it's kind of upside down. All right, so that is going to be y equals negative 35 cosine pi over 6 t, and our midline is at 40, so this is plus 40. Okay, and there you have it. Go enjoy riding Ferris wheels. I think you guys will probably never ride a Ferris wheel again. Or if you do, you'll look at it a completely different way. That's supposed to be a clover. You get the idea. Peace.